Okay, so I think we can start. So welcome everyone to this week's machine learning coffee session. So this week we will have Professor Andrew House presenting on computational rationality. And if you have any questions, please can you reserve them to the end of the presentation. So please, Andrew.
Thank you very much. Yeah, I'm happy to take informational questions as we go through, just for clarification, but not discussing the questions. So thank you for inviting me. I first want to say I'm a cognitive scientist, not a machine learning researcher, and you'll see the evidence for that as we go through my talk. I also want to say that I'm aware that you had a talk presented to you by Elisabetta on computational rationality just a few months ago, and so I've decided to do something a little bit different in this talk, and a large part of the talk will not be about my work. It won't be just an introduction to computational rationality, but rather I'm going to try and push the boundaries of understanding how computational rationality can be applied. And so there's a bit of risk in that. And so if the talk tanks, I apologize now, but we'll see how it goes. Okay, so the figure on the right of the screen gives an overview, and the contents of that figure will become clearer as we go through the talk. One of the questions that's fascinated behavioral scientists, including psychologists, over many years is the question about human rationality. Are people rational? And there are various conceptions of rationality applied to biological agents and humans in particular. Bounded rationality is one, ecological rationality. This is the strong view that people actually are not rational in any sense, but rather they're biased and irrational. And in this talk, I want to discuss this different conception of rationality, which my colleagues and I call computational rationality. So I'm going to introduce the idea, offer a formal definition, look at some examples, and briefly discuss the implications for interactive AI and theory testing in cognitive science. The figure here is a Heath Robinson, a British cartoonist who became famous. His name became a byword in the UK through the 19th century for these overly complex and apparently irrational machines. And I've put it here, actually it's sort of a mixed message in some ways. I put it here because in part, I think we can do better than this as behavioral scientists in theorizing about humans and the nature of cognition. But also because there's a perverse logic to these machines. The reason that they're fun is because if you work through them, all the pieces fit together, and despite the complexity, they actually form a functioning machine. And that functioning machine, however complex or simple, is something that's often missing from theorizing in the behavioral sciences. Okay, so introduction. I'm just going to introduce it with a series of very simple examples that illustrate forms of rationality, forms of computational rationality. So the first is adaptations to memory limits. So if I give you a phone number to remember, some of you will have the amazing capacity to remember the whole thing in one go, and to write it down by just looking at the number, reading the number through once, and then moving to a piece of paper and writing the number on that piece of paper. However, it's more common that you'll split it into chunks, and so you might split it into two chunks. And I suspect that a good proportion of the audience now will be able to perform that task. Just remember the first part, write it down, revisit it, look at the second part, and then write that part down. More commonly, though, people split it into three chunks of 3 and 4 digits. Some people will split it into 2-digit chunks, and some will even split it into single-digit chunks. So there's an explanatory problem here for a cognitive scientist to understand why do you get that variation across individuals in the way in which the people choose to perform this task. And actually, if you measure people's memory capacities and then ask them to make choices about how they perform this task, you find an extraordinary correspondence between the predicted optimal strategy, given a speed accuracy trade-off, and the strategy that people choose to perform. So the bounded optimal strategy here in Russell's sense, Stuart Russell's sense, corresponds to the computationally rational strategy. It's computationally rational in the sense that it's the best thing to do given the limited machine that you have available to you. Okay, similarly, we might ask about adaptation to motor uncertainty. So motor uncertainty is your ability to get your motor system, your manual system, for example, your hands or your eyes, to actually move to where you want them to move to. And so we can say, as you can see the Viber icon in the middle of the screen, and the question you might ask is, where should you aim if you want to select the Viber icon? Given that you're not actually going to exactly hit your aim point, but rather there's some Gaussian, bivariate Gaussian, there's a bivariate Gaussian distribution of noise around that aim point. So the noise here is represented, so say 3 standard deviations by this grey circle, but you should aim for the center of the icon. Okay, so now if I ask you to aim for the photos icon, where should you aim? And the answer is that you should slightly offset that aim point. And the reason here is that the costs of hitting in this case, the WhatsApp icon are higher than the costs of missing to the right completely. Because there's an error recovery cost. If you hit the WhatsApp icon instead of the photos icon, then that application opens and you need to close it back down again. And so the computationally rational strategy for people here is sensitive to the motor system noise. And there's evidence that people are very finely tuned to that motor system noise in their performance of motor system tasks, such as this. So here's some of the evidences from a work by Tromshausen, Maloney and Landy in 2008. And they set up an artificial version of this task with, rather than icons, red and green circles, each of which had a point score associated with them. So you get plus 2.5 points for hitting the green circle and minus 12.5 for hitting the red circle. And they measured people's performance on these tasks, and including, most importantly, measuring their motor variance and where they actually choose to aim given different cost structures in the environment. And so you see on the right here a plot of the optimal shift against the actual shift, where each plotted point represents a single participant. And you see this extraordinary correspondence between the optimal shift and actual shift that individuals use, given their own individual profile of motor noise performance. And then the third example is an adaptation of decision-making strategy to information access costs. So those first two tasks are relatively low level and straightforward. You can think of them in terms of decision theoretic terms, in terms of control theory about what people are expected to do, and therefore calculate and make predictions in a quite straightforward way about what people should do. But let's look at when people combine the lower level functions of their motor system and visual system into strategies for performing higher level decision tasks. So you need to rent an apartment for the remainder of your stay in Helsinki, and those apartments might be presented in a tabular form. So each apartment in a row, and the attributes of the apartment in columns here. And then you can make a choice by selecting one of the buttons below apartment A or apartment B. This is a simplified version of the real world task. Which attributes should you consider? Well, of course, you've got your own latent preference function over those attributes, and so you're going to look at some of those things. And if you might think, if you behave according to the axioms of probability theory, that you'd make independent assessments of each of the apartments and then choose the one with the highest expected value. The evidence for that suggests people do something slightly different. So this is eye tracking data for what people look at when they make this kind of choice. And it's just data, it's just evidence. It doesn't give us a direct microscope to look at what's going on inside, but it gives us some evidence about what's going on inside the head. And you see that one interesting feature of the eye movements is, firstly, there are a lot of them, and there's a lot of items are fixated, and in an apparently unsystematic pattern. But one systematicity that does show across all of the participants, this is just one participant's eye movements, is a tendency to look at intra-attribute values, sorry. So if you look at distance, then this participant looked between the 27 minutes distance and the 12 minutes distance backwards and forwards twice. Similarly, but in safety between average and unsafe. So what the participant is not doing is going along the rows and weighting the values and then adding them up to give an expected value for that option. Rather, what they're doing is a lot of comparison within attributes. Now, when instead of allowing the participants to look at the items immediately, you cover the items, and they need to click on them to reveal them. It's an artificial interface, but nonetheless one that is not uncommon, where you need to act on the interface in order to reveal information. When you do this, you get a very different pattern of information access, and it's dominated here by intra-option search rather than inter-attribute search. And so the participants, they access less information, that's less interesting, but they also access information in a radically different way. And so they scan along, you see along the top row, they consider all of the options for apartment A, and then they go along the bottom row and they consider, sorry, not all of the options, but some of the options for apartment A, and they go to the bottom row and they consider some of the options for apartment B before making a choice. So you get a change in the information, gathering strategy in response to the cost structure of the task. We've, with my colleagues, Shirley Chen, who I think is in the audience, have modeled this task and shown that these kinds of changes in higher level decision strategy emerge from variation in the underlying performance constraints on the task. And then you will also get adaptive planning. So not just decision making, but also adaptive planning in human behavior. One of the most famous examples of this is from Tetris, where the planner, or when a human performing this task needs to project, to make a decision about how to rotate the block and how to move it laterally in order to optimize its position when it falls into the existing blocks that are there. And you might think that internal planning, imagining the future sequence of events in your head is necessarily lower cost than planning in the world, what are sometimes called epistemic actions, so rotating the block in the world in order to imagine what's going to happen when it falls. And therefore that people wouldn't use epistemic actions in this case as a highly placed task, and you'd think that they might just use internal processes of mental simulation in order to figure out how to rotate and translate this particular block. In fact, the evidence is against that. People, even experts, make extensive use of epistemic action, so that is planning in the world, in order to solve this kind of planning task. And so there's a trade-off between internal and external planning. And fascinatingly, that trade-off is something that people appear to solve adaptively, that is, in some sense, optimally, that they adjust their internal and external planning in response to their own constraints, their own cognitive constraints, and also the cost structure of the task environment. So O'Hara and Payne tested this view, and here's the 8 puzzle. You've got a start condition on the left and a goal position on the right. And what they showed was that if moving the tiles has a very low implementation cost, then people tend not to do much internal planning. They use the external resource in order to perform the planning task. And so they move the tiles around quite rapidly to try things out. As soon as when you start to increase the implementation costs, you make the tiles a little bit sticky. and it costs maybe half a second to move the tile 2 here down one cell. Then people start to do more internal planning, and that means that fewer external actions in the world. It means more time thinking, less time acting, and it also means changes in the representational structure of the problem. So as they do more internal planning, it's suddenly they start to realize, oh, I can re-represent the problem not as just as individual tiles, but rather as chains of tiles, and that helps them solve the task in novel and more efficient ways. Okay, so why are those examples relevant to computational rationality? Well, they're all examples that I presented in an informal way, but they're examples that can be formalized, and they're examples of where behavior can be predicted by assuming that humans are computationally rational. So this is the idea that theories of cognition can be specified as optimal program problems. And I really mean program. I mean program in the computer science sense of program, so optimal program problems, where that problem is defined by an adaptation environment, a bounded machine, and a utility function. And those were the three components on the overhead, the very first overhead that I presented. I'll show that again in a second. So it's called computational rationality to emphasize the incorporation of computational mechanism into the definition of rational action. So rationality is not, for humans, computational rationality. If humans are computational rational, it's not about behaving rationality just with respect to the ecological environment. It's not about just behaving rationally with respect to your utility function, but rather the definition of rationality has to account for the limited resources that are available to people. So this is a graphical illustration of the idea. So there's a specification of a utility function, there's a specification of an adaptation environment and a neural machine. And the constraints from those three sources define a space of programs. A space of programs that will run on the machine in the environment and which will satisfy the utility function. And of course, there's a set of optimal programs, bounded optimal programs within that space, those that maximize the utility function. And it's that set P star which should be used according to the theory in order to predict what people will do. So people don't just pick random programs in that space of programs, rather they work through learning, through various forms of learning towards acquiring a bounded optimal policy. Okay, so some of the context here is that this idea might seem completely crazy to you, or it might seem too obvious to be worried about. So I want to put it in some historical context, and this territory has been fought over 70 years, nearly 70 years. Ward Edwards, very early on with behavioral decision theory, really committed to a notion of economic rationality in humans, which said very little about bounds. Herb Simon reacted to that with a notion of bounded rationality, and said, well, look, hang on here, humans are highly bounded, and we really need to think about people as being boundedly rational. There's a notion of there's a notion of rational analysis introduced by John Anderson, which shifted the debate for many years towards a sense of, towards a conception of humans as being understandable in Bayesian terms at the very highest level. So it's really a way of trying to understand how humans behaved mostly in terms of the ecological adaptation environment, and trying to figure out what people should do given the structure of the environment. From machine learning, we can borrow the notion of bounded optimality, which is essentially what we're doing here with computational rationality, and saying, well, hang on, the way to view rationality is in terms of the limits imposed by the machine as much as the limits imposed by the task environment. There are modern versions of bounded rationality. One's called ecological rationality, Gergenser, which makes a very strong commitment just to the ecology and misses, in my view, what Simon referred to a theory is in terms of pair of scissors. And so one blade of the scissors is the ecology. The other blade are the resource limits that humans are subject to. Gergenser focuses very, very strongly on the ecological rationality. There are ideas from cognitive game theory and also adaptive interaction in human-computer interaction. And it's no accident that many of the examples that I give derive from human-computer interaction. The idea also predates resource rationality, Gershman's computational rationality, and reward rationality, as we see in human-robot interaction. But I think shares very much indeed with those ideas. Okay, so the idea contrasts the view that people are irrational, biased, and that need nudging to behave rationally. And this is perhaps the strongest contrast, and one that I'll develop a little bit further in the remainder of the talk. Okay, so a formal definition. So together, an adaptation environment, information processing machine M, and a utility function U fully specify an optimal program problem. Solving the problem requires identifying the set of optimal programs P star, defined by the following bounded optimal equation, which is adaptive from Russell and Subramanian. So for machine M, the set of programs P star is the set which maximizes the utility expectation U over histories H over behaviors sampled from M and P in E, where E is sampled from the distribution of adaptation environments. So the inner expectation over here is over histories, what the agent actually experiences as it behaves in some environment, and the outer expectation is over a distribution of environments. So the claim is that this formalization of the problem faced by humans is useful in order to model humans, perhaps in interactive AI systems, but more directly for us in its original conception for modeling humans in order to develop a theory of human psychology. So we've developed that idea in a series of articles over the years, and they have increasingly made use of a POMDP conception of how to take that formalization through into an implementation in a computer program that we can then use to simulate human behavior and make predictions. Okay, so the idea of using POMDPs to model humans, I think first introduced, as far as I can figure out, by Dora and Diane in 2008. And the key move that they made and that we sign up to as well is that the transition and observation function define a bounded machine M and an environment E. Unfortunately, they're sort of combined together into those two things in the kind of raw formulation of the POMDP. But nonetheless, that's where the theory goes. And so then what the agent is doing is it's like the little part at the center that's responsible for finding bounded optimal programs, bounded optimal policies, given the constraints imposed by M and E. And so obviously U is defined in the critic, and P star then approximates is then an approximate solution to the problem. Okay, so a critical thing here is, and so this is that the cost of optimization is paid by the modeler. The hypothesis is not that humans have to perform these optimization functions. There are various ways in which they can acquire strategies. And for the moment, what the claim is that you can make useful predictions of human behavior using these systems, not that the learning process that people go through corresponds to the learning process required to find P star. So in this sense, much of the machine learning is below the line theoretically. So so P star can be found using any technique, whether it's Q-learning or DRL, etc. But that makes no difference to the psychological predictions. That view, I think, is getting harder to maintain as as the machine learning methods develop, it's very difficult. For example, the boundary gets blurred with long-term, short-term memory, and it's unclear there where what the theoretical role of LTSM is in making these sorts of predictions. Okay, so my talk is far too long. I was going to look at 3 examples in detail that I see as being at the cutting edge of the application of computational rationality. And I'm only going to have time to do one of those, I think, probably. Let's see how it goes. I've still got to 9:45, so, okay. The 3 examples illustrate how complex, apparently irrational behavior can emerge as a consequence of computationally irrational adaptation to the constraint problem defined by a machine, an adaptation environment, or utility function. And also that it's difficult, probably impossible, to understand higher level cognition, e.g. decision making, problem solving, and causal reasoning without understanding how it's dependent on P star and therefore on M, E, and U. And it was the second point that really motivated me to structure this talk in the way that I have, because there's this constant tension that's been in, that you can see in cognitive science really since its inception, that people who want to study higher level functions like reasoning, they don't want to be bothered with motor control and perception. It seems like an irrelevance to them. What really counts is deep reasoning that people can do when they just think about things. And unfortunately, I think one of the lessons is, and I think, and hopefully this lesson was partly evident in the first 3 examples that I gave. One of the lessons is that when people perform higher level tasks, they're bounded by the neural machinery that they have available to them, and they're bounded by their experiences, and they're bounded by evolved utility functions that determine what's important to them. And so their ability to reason is constrained by those things, and it's very, I think it could be misleading to focus entirely on reasoning and not to take into account the fact that reasoning has to happen on some physically instantiated machine, and the behaviour will be jointly shaped by the constraints that are imposed by that machine and by the requirements of the task, of the high level task, essentially. Okay, so we return to this figure here, and so the 3 examples. One is of intrinsic reward, which is an example from machine learning by Sorg, Singh, and Lewis in 2010. The neural machine is an example of sampling under uncertainty, sampling with noise from a memory system. And I looked in particular at Costello and Watts in 2015. And then the other one is the experience of randomness by Hahn and colleagues in 2009, which illustrates the importance of the adaptation environment. I think, given the time limits, what I'll do is just have a look at the sampling with noise, the Costello and Watts, which I think is interesting. So let's just skip forward a little bit. Okay, so we're looking at the constraints imposed by the neural machine on probabilistic reasoning. So consider the conjunction fallacy. Linda's a 31-year-old, simple, outspoken, very bright. She majored in philosophy as a student. She was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. So which of the following statements is more likely? Linda's a bank teller, Linda's a bank teller and active in the feminist movement. So the conjunction A and B. So Tversky and Kahneman in 1993 found that in some cases more than 80% of participants ranked A and B as more probable than A, violating the conjunction rule. So the greater the difference between P and PB, the more frequently people exhibit the conjunction fallacy. Also the greater PA given B, the more frequent the fallacy. So at first blush, this seems clear evidence that people are irrational, right? They're not following the rules of probability theory. So what on earth can be going on? Here's another example. This is from Costello and Watts, and just demonstrates that there's sometimes a tendency to think that the problem here arises because of the oddity of the Linda example, but this is an example where Costello and Watts gave quite a large number of participants reasoning problems, probabilistic inference problems concerning the weather in Ireland, which is very similar to the weather in the UK, and it's quite often cloudy and rainy. But you see the rate of conjunction fallacies here. Some of them are extraordinarily high. 80% of their participants exhibited a conjunction fallacy given the problem to determine whether it's the probability that it would be cold and rainy on any particular day. 68% for cold and thundery, 72% for cold and icy, etc. But there is a pattern here. And so some of the conjunctions are people exhibit the conjunction fallacy much less frequently for. So for example, sunny and snowy. And Costello and Watts claim that they can predict which of these conjunction fallacies will be exhibited at higher rates, given the assumption that people are using probability theory, but they're doing so using a bounded memory system. And that memory system is one in which they can only sample instances from, but the sampling is noisy. So there's a chance that any particular sample, say of a rainy day, is returned as a dry day and vice versa. So let's just skip over this overhead. Just a little bit about their theory. So, and I'm going to try, I've reached the end of my half now, so I'm going to try and wrap up in 4 minutes, if that's okay. So it's probability theory plus noise. So the theory is that people randomly sample events from memory, counting the number that are instances of A and dividing by the sample size. Obviously, straightforward. Human memory is subject to various forms of random error, however, in that process. So assume that events have some chance, d less than 0.5, of randomly being counted incorrectly. There's a chance d that a not A event will be incorrectly counted as an A, and the same chance d that an A event will be incorrectly counted as a not A. So the expected value for a noisy estimate for the probability of A is 1 minus d times PA plus 1 minus PA times d, as you'd expect, just probability theory. But because of the nature of that memory system, so imagine you're asked to drawing bags from a ball, and you're asked to estimate the number of green balls, but you're sampling this time, not as in the usual circumstance, sampling without noise, but you're sampling with noise. And so some of the green balls actually come out looking red, and some of the red balls actually come out looking green. Here I've illustrated that with a noise parameter of 0.3. And then what happens is that you get a systematic bias due to that noise in the sampling process. A, it's noisy, and that's useful to know, and B, it's going to regress towards the mean. So you will tend to, there are a large number of green balls, you'll tend to sample fewer green balls in your noisy sampling process than there actually are. Your sample will be smaller, and for the red balls, you're going to sample more than are actually there. And so so your estimate of the probability of A is always going to be shifted towards 0.5, whereas irrespective of whether it's PA is small or PA is large. And the smaller PA is the bigger the shift, and the larger PA is the larger the shift. So you get this regression towards the mean. And that explains a range of apparent irrationalities in human decision making. So Costello and Watts show that probability theory plus a machine that supports sampling with noise from memory can explain a number of apparent biases, including the conjunction fallacy, underconfidence, overconfidence, subadditivity. And in my own work, we've shown similar sorts of effects for context effects, which I'm not going to go into. So people are surprisingly good at following probability theory given the bounds imposed by E and M. Okay, so I'm going to skip forward now to over this example as well. It's a summary. So it's very hard getting a half an hour talk. 15 minutes is, you know what you've got to do in 15 minutes, you know what you've got to do in 50, but 30 minutes, wow. Okay, so discussion summary. I've introduced the idea of computational rationality. Complex, apparently irrational behavior can emerge as a consequence of computationally rational adaptations to the constraint problem defined by a machine, an adaptation environment, and a utility function. And apparently irrational actions are taken by optimal programs P star. I haven't really had a chance to go into that. It's difficult, perhaps impossible, to understand high-level cognition, e.g. decision-making, problem-solving, causal reasoning, probabilistic inference without understanding how it's dependent on P star and therefore how it's dependent on ME and U. And I wanted to look at 3 examples, but I've looked at one of those. So only the third example illustrates the crucial optimization step. I can go into that. The other examples illustrate the potentially counterintuitive nature of bounds, the possibility that higher level probabilistic reasoning agents with noisy neural machinery and trained in realistic adaptation environments can offer useful models of humans. So future work should, I think, look at integrating these bounds into reasoning agents that offer more general models of human cognition. Thank you very much.
Okay, thank you, Andrew, for the very interesting talk. Are there any questions? We still have good time.
Yeah, you can. Anna.
Hello. I want to ask you something about basically from psychology. We know that people do have biases, that, for example, like they tend to work with people whom they like, and they tend to do a lot of things for people whom they like. Is this explained by this theory?
I think that a lot of those apparent biases are now challenged, and that so there are a couple of recent papers that really overturn long-held assumptions about the nature of bias. And so one recent paper by Gagarinza is called "The Bias Bias." It says that behavioral scientists, particularly behavioral economists, have now developed a way of succeeding in a research culture by looking for biases in people. That's the kind of thing you say, oh, wow, look, I've identified a bias. And it's become a truism that people are biased. And actually the evidence is often quite weak. Now, I don't know about the particular case that you have described, but many of the things, of the central ideas about the heuristics and biases agenda have now been shown to be, the central ideas have been shown to be false, I think. I think another thing is that very often a bias in and of itself is not an explanation. So it's clearer perhaps with the notion of suboptimality. Suboptimality is not an explanation, it's the absence of an explanation. And the science demands that the reasons for the presence of that apparent bias are revealed. And that's, I think, the current direction in the literature.
Okay, any other questions? So I have a question. So I started to wonder, sort of, can humans sort of protest against the tasks or the settings given to them? So for example, on the bank teller example, the human probably doesn't want to think in terms of just having exactly 2 choices, and then might not sort of enjoy the whole setting, and then that might imply on how they think and answer. So are there these kind of considerations?
That's a good question. So I think probably not that so that with the Costello and Watts study, with the weather study, 2 of the participants answered all of the questions the same way, and they were excluded from the analysis. But maybe the fact that they answered all in the same way was an objection to the structure of the question, right? But that's very common in human psychology experiments, that only participants that the way it would be justified is only participants that have understood the question as put in the experiment are included in the analysis. But that can lead to very high rejection rates, and there's very little analysis of what people, those people who have not followed the instructions are doing. I think one antidote to that is the analysis of individuals. And one of the things that, in fact, that we've done in our past research with computational rationality is to try and model every individual participant, not to model the aggregated data. And I think that's a crucial step in moving to more fully embrace that variability.
Okay, yeah, that makes a lot of sense. Thanks.
Hi, Andrew.
Okay.
Hi.
Yeah, please go ahead.
How would you kind of, or maybe the question is, could you recommend some recent papers that kind of look at this from both like the individual perspective and then the evolutionary timescale and social perspective? Like what kind of, let's say, utility function components emerge, or can they be made to emerge from that, like intrinsic motivations and basic psychological drives that could be explained through evolutionary and social mechanisms?
That's a really good question, and no, I can't. I think so. So one of the things I was trying to push at in this talk was to say that particularly intrinsic motivation is something that is underexplored. Psychology is focused mostly on the bounds of the neural machine. There's also work on the ecology of task environments, particularly at the Max Planck in Germany. But the intrinsic motivation from a computational perspective is just horribly neglected. We really don't know anything about those utility functions. And so the example that I was going to give is the work of Satinder Singh and Rick Lewis and colleagues at Michigan on intrinsic motivation, but it's very much in a toy world. It doesn't make contact with human data. I think it's exciting and interesting, but that kind of theory needs taking into the psychological world. I think actually maybe another example. There is work, obviously work which I'm not an expert on at all, but in economics on the nature of utility. So I'm thinking of work such as Ernst Fair in Switzerland. So there are some examples like that, but they tend there again not to ground the theory of utility in a theory of the whole functioning machine that has both a mechanism for computing something. It has a utility function, and it operates within ecological environments. And it's the combination of those three things, I think, that will have to define the future of how we take cognitive science forward.
Okay, any other questions? I think we still have time for one short question. Okay, if not, then I think we will conclude the session. So thanks for the speaker again. And we will continue next week when we will have Antti Hyttinen presenting. So thanks everyone and have a nice day.
Thank you.